Let's try out the new Inception Mercury V2. So let's just ask it to repeat this text exactly. And what exactly is this text? This text is actually from the Large Language Diffusion Model paper, and I want it to repeat it. So let's take a look. Oh, what's happening? Okay, I shouldn't have asked for web search, but look at that. Look at this. Look at this. Look at this. That large chunk of text coming, and oh, it's done. Less than 10 seconds. And okay, where does it end? It end with acknowledgements. This was supported by the National Science Foundation of China, 924701118. Let's take a look at the end here. 924701118. Okay, that is 20220484044. So yeah, it got it right. And over here, let's take a look at the top. We have Kaoling School of Artificial Intelligence. So let's take a look at that. And here we have Kaoling School of Artificial Intelligence exactly there. Hi, everyone, and welcome to today's session. Today will be a very interesting session on Mercury 2. So this is basically a new style of large language models that instead of generating a token one by one, like the cat sat on the then mat, instead of generating one token at a time, what this kind of model does is that it generates all the tokens at the same time. So you must be thinking, wow, that's crazy. How can it generate the tokens at the same time when it doesn't know what's before? So this is the beauty of such a diffusion model. It generates the tokens all at the same time, but it need not be correct, you see. You only have a few that you are sure that, these are correct. And then you slowly, as you iteratively generate with whatever you have in the previous iteration, you slowly get towards the correct answer. So there will be a visual illustration of this later. The idea is that by iteratively predicting a less noisy version of the initial output, we slowly get the output. So this is very similar to diffusion in images. You start with an image of noise, and then you slowly start to predict, like, let me just illustrate here. You start with an image where it's all random noise, and then maybe the random noise after one iteration, it considers its neighboring pixels and everything, and then it slowly becomes like this shape. And then eventually, after you go through multiple iterations, you might end up with maybe a circle. So that might be your intended image. You start off with noise, and then you slowly, through each step, you slowly go towards the target output. So for example, if your target output is the cat set on the mat, you might be like the garbage, 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 set, garbage, garbage. Yeah, it might be initially like that. And then after that, it might be the cat, set, garbage, garbage, mat. Then after that, eventually you have the cat set on the mat. So essentially, we can predict the entire sequence of tokens all at the same time, but you retain some form of caution. Like you don't just say, I want to predict everything at the same time. No, we say, okay, I think these few tokens are a bit more sure. I'm a bit more sure of all these tokens. So I predict those tokens first. And then after that, using this as my template, I like, the blank, blank, blank set, blank, blank, oh, I think it might be a cat. So, like, so you fill in the word cat and so on. So it is something very, very similar to, like, I guess how we do fill in the blanks. So this, if you actually read a paper called BERT, like bidirectional encoders for like transformers, essentially BERT has something similar, like they do some masking. So like maybe you have the mask set on the mat. Then you try to predict the mask word, and you try to predict the mask word, which is cat. Okay, but this whole diffusion model is way bigger and way larger scale than BERT's, because BERT, typically only predicts like maybe one mask at a time. This over here, this diffusion model here, it can predict everything at the same time. So this is really, really cool. And what does this mean for you? All right. What this means is that right now, if you ask like ChatGPT, Gemini, or Claude to generate like maybe a 1 million tokens, yeah, you might need to wait for say a few minutes, 2, 3 minutes. If you use such a model, assuming the context length can be, I mean, the output length can be 1 million tokens. If you use such a model for diffusion, easily you can have 5 to 10 times the speed up, which is, you know, going to be less than a minute. Yeah, so this is significant, especially when we have a lot of agentic workflows. Now, a lot of people use agents for coding, for automated daily tasks. And if you can imagine, if the LM can reply to you 5 to 10 times faster, can you imagine how many more things you can do? So these diffusion models are in the same spirit as the large language models because they are still a transformer, but they predict much faster. Okay, so I hope I've gathered your interest here. This is game changing, I can tell you. This is game changing. If we can do something like this, there will be so many more applications. Like, can you imagine doing deep research in less than a minute? Right now, it takes 10 minutes, right? 10 to 20 minutes on OpenAI or Claude or Google or Gemini. Yep. Imagine if you could do that in 1 minute. And diffusion models can help you to do that. Yeah. So this is Mercury 1, all right? Mercury 1 was created last year. So this was the first version by Inception Labs. And you can see that just this Mercury 1, you can see this is the coding index, like how good it is at coding. It can rival like GPT-4o mini, all right? And yeah, over here, the output speed here, if you can look over here, this is very close to maybe 700. And if you look at like GPT-4o mini, it's about, I don't know, 50. Yeah, so this, you can easily see about 5 times, 10 times speed up, just this small. And then if you just look at this mini, the coding performance is not that great, but it's sped up even more. This is 1100, this is like 20 times speed up. So you can see easily, the performance doesn't degrade that much, okay? But you get such a massive speed up, all right? So that was last year. All right, this year, this is the information from the Inception Labs blog. You can see the link below here. This basically is what we have now. Now we have like 1,000 tokens per second for Mercury 2. And like the next best speed is like 89 for Claude Haiku 4.5 and 71 tokens per second for GPT-5 mini. And over here, they advertise it as 5 times faster than its competition. But actually, if you look at the stats here, it looks more like 10 times or 15 times faster. So this is really game changing. It really makes your output token count much, much better. All right. And you can see that the price is also very cheap. Later, I have a slide to show you like how cheap it is compared to autoregressive models, because you just need to do fewer iterations of the model to generate this. So you don't have to run your GPU as much. As such, your output tokens can be much cheaper. And you can see that it's it has reasoning, which is quite impressive. You can do reasoning with diffusion as well. The context is not that great, but it can do tool use. It can do structured outputs like JSON. So you can use the same paradigm that you train your large language model with, because essentially the input-output sequences are the same. It's just that instead of trying to predict token by token, you predict the whole thing at the same time. Right? So you can use exactly the same data sets that you have for normal transformer or normal large language models training. The only difference is how you do your inference. Right? And also your loss function will be a bit different because you are predicting all tokens at the same time. You have a slightly different loss function. So let's take a look at the Mercury 2. So this is Mercury 2. As you can see, Mercury 2, the scores are way better. Like you can see that all of this, assuming that all these are the bigger the better. All these scores like GPQA, this is for science. I think this IF is some logical data set. This AIME is math. I think this is the tool assisted database, tool assisted usage, I think. I can't remember the name of this, but this is to do to use. So essentially all these data sets, I can't remember what's LCB, but all these data sets, they actually help to show that a diffusion model is just as good or even better than standard transformer autoregressive models. You can see it like it's just as competitive. Maybe like Gemini might do better for some of them, but overall you can see the scores are very competitive for Mercury 2. And it's much cheaper. So you can see over here, this is 75 cents per 1 mil output token. You compare to Gemini 2.5 Flash, which is cheaper than Gemini 3 Flash. Is $2.50 for 1 mil tokens, and GPT-5 mini, which is like the cheaper version, it's like $2 per 1 mil tokens. Yeah, so this is quite significant. You can see that it's like 3 to 4 times cost savings. So not only is it faster, it's cheaper also. So I also tried something like, I was thinking, what if, if you do predict all tokens at the same time, can you still remember the sequence order and so on? So I tried to ask Mercury 2 to try to, repeat one sentence like this. I also tried longer sentences and it worked. Like I tried an entire Wikipedia article and it still managed to replicate it. I just chose this sentence because it's easier to show in one slide. So you can see that it managed to preserve the entire sentence here, which kind of shows that although it's predicting all tokens at the same time, it doesn't really compromise on the sequence of your tokens. So this is quite impressive. All right, and I actually wanted to show you a live demo of this today, but the site is a bit down right now. I think there's too many subscribers to this Inception Labs right now. So maybe you can try it on your own. Maybe a few days later, there might be fewer users and you can try it. Definitely quite impressive. So if you try it out, if you can also on the diffusion effect and they will show you like how the tokens change over time. It looks like this. So let me show you how it looks like. So assuming that all these are random tokens at the start, like these are called noise. Okay, what we do is we iteratively, confirm certain tokens and then we keep trying to predict the rest. Let's just show the illustration. Okay, so you can see that autoregressive model do it one by one is very slow. And the parallel generation, like the Mercury at the top, it really generates everything. And all these things in dark blue are the confirmed tokens. So you can see initially the tokens are like a piece of garbage. If you look here, Z Mango, all this, like this is what you do when you decode the embedding space back to the token space. You don't get anything that makes sense. Okay, but maybe you get the quick and the lazy over here. They confirm rather early because maybe these few tokens have the highest confidence. So we say we lock it in. Okay, this token is very good. It is in this position. Then you ask yourself, these few tokens in the middle, how do we fill them up to make sense of based on the input prompt? How do we make sense for the output to how do these tokens need to be in order for the output to make sense? So then we ask ourselves that, we try to get the model to generate again, and then maybe the next token that is most significant is jumps and dog. So it's like, okay, the quick something something jump something something lazy dog. Then we try to fill in the next few tokens again, and you can see after a while, it confirms everything. So this process takes a few iterations. It's not like one shot, hey, everything is out. So essentially, it can mimic the kind of job that, have you imagined, like, for example, you do a kind of agentic workflow, like we ask, like, what is 1 plus 1? Okay, then maybe your first answer is 1 plus 1 equals to 3. Then after that, your reflection could be like, actually, 1 plus 1 is equals to 2 instead. Hence, 1 plus 1 equals to 2. Or maybe, instead of reflection, some models might say, wait, stop, or something like that. Yeah, so this is the kind of like once you do autoregressive, sometimes you generate something wrongly and then you want to say like, I want to change again, but I'm trapped there because I already confirmed that token. So something like this, maybe if you were to do the diffusion here, what will be confirmed is 1 plus 1 equals 2. And then the last token that will be predicted maybe is the answer. So, you don't have to do like a recorrection because you have sequentially generated your tokens one by one. You already, sorry, you already generated the earlier tokens before. You already know, like, okay, this one is going to be something that I will do last. All right. So you don't have to do something like this, like where you correct yourself before, because as you generate the tokens in the diffusion model, the tokens that are generated last are usually those that require more time to process. So I think you can skip on all this like reflection and so on. Yeah, so this is my own take on this. Of course, if you generate wrongly at the start, let's say something like this, you generate wrongly, instead of jumps, you generate swims, when this is not supposed to be swims. There is a mechanism that allows you to change this token back to a mask token again, and then you can regenerate that prediction as well. So, there's some failsafe. So in general, this is how a diffusion model works. I'll just stop here for a while because this is a more layman definition of how it works. I'm going to go through the equations and some other visualizations later. But just a quick pause here in case you want to ask anything before I go on. Okay, all good, right? Then I'll proceed. Okay, so these are some of the illustrations of the diffusion language models. I've taken it from some YouTube videos. You can watch them as well. The video names are down here. So essentially, what are diffusion models in a more like technical sense? A diffusion model typically has two processes. Okay, the first process, of course, is you need to use some fixed way, maybe adding some latent noise, some Gaussian noise or something. So, like for example, for a stable diffusion, um, this is for images. What we do is we start off with our target image, a very nice image, and then we slowly add noise to it, and then we slowly add noise to it, and we slowly add noise to it. So this noise adding process is already known, okay, because you are the one to add in the Gaussian noise or Dirichlet noise or whatever noise you want to add in. You are the one who adds it in to perturb your image. And the cool thing about this is that as you add more and more noise, okay, in the end, your final image should be something. Okay, make sure that your final image is is a complete mess. All right, you must make sure that it's like that. You cannot see the image at all. Okay, why? Okay, because the key to diffusion model is the reverse process. So you can see this reverse process over here, right? The idea is that if I make my final image a complete mess, and I can still train my predictor. So this backwards part is your predictor. Predictor from noise to less noise. All right. So if I can make my final image a complete garbage, and I can train my predictor to predict from a noisy image to something that contains less noise, and from a less noisy image to something that has even less noise, and then after that, from even less noise to completely perfect and beautiful, then you have a diffusion model that can essentially take in complete noise and get back a very nice image. Okay, so this is essentially how a diffusion model works. So you have this completely garbage noise and you slowly diffuse such that your final image is great. So learning this predictor is the key to a diffusion model. So typically what we'll take in is you will take in the noisy image and then you output the less noisy image. And usually when you take in here, you also have some conditioning variables, for example, the prompt and so on. So you could condition the image to be more and more like maybe a anime character in this case, or you can condition the image to be something like a sports car. Then from complete noise, it will generate itself slower and slower towards an image of a sports car. So essentially, this is how a diffusion model works. You train a predictor or denoiser or denoising network to predict an image that is less noisy and conforms better to the conditioning variables. So essentially, this is the crux. Okay, you don't predict one shot from noise to the final variable. You slowly morph it into the final shape. And in so doing, you can help to better refine the features. And if in the end, the final image is very crisp because it has been refined iteratively and not just a one-shot process, right? So similarly, can we do the same for text-based tokens? Okay, instead of doing image as the input, actually all these images here, at the core of all these images, the images are like pixel values. Okay, so over here at the core of it, what we can do is, we can also do diffusion. Can you do diffusion on token embeddings? Okay, the embeddings itself on embedding vectors. And the answer is yes. We can also do diffusion process. Okay, not just on these pixel values. In fact, these pixel values, if after that, it will be converted to embedding vectors as well. So if you use something like what do you call that? Vision transformer or something similar, you can convert the patches into embeddings. So your images will be split into patches, and then you have the embeddings, and then you can do the diffusion on the vision transformer embeddings and so on. So essentially, if your image space eventually goes to embedding vectors, Your text space also goes to embedding vectors. In fact, not just text, audio space. Okay, you can also make it to embedding vectors. And if everything goes to embedding vectors, can you just corrupt your embedding vectors to make it very, very noisy? And then you try to learn the predictor to make it less noisy again, to get back your original format, original text, original image, original audio, and so on. It turns out that yes, you can do that. And this is significant, right? It means that we have unlocked multimodal diffusion. Okay, why I say multimodal diffusion? Because this diffusion process works on embedding vectors. It works generically across all modalities. Okay, if you have a touch modality, you can convert to embedding vectors. You can do diffusion on it. Audio, you can do diffusion. Um, Vision, you can do diffusion. Video is a mixture of images and audio, so you can do diffusion on it as well. So essentially, any modality you have, any of the five senses, maybe taste can be converted to embeddings as well. You can definitely do diffusion on it. If you have a fixed way to corrupt your embedding vectors to become worse and worse off, and then you train the predictor to get back to where it originally was, you train it on enough data sets, essentially you can generate almost anything. Yeah, so this is really cool. Who knew that like something like stable diffusion on images could one day be applied to large language models? Who knew that? Yep. And that's the cool thing about research, like we keep trying to combine things and eventually you find something that works. So this is the illustration that I was talking about. You have a very, very nice and clean embedding and you slowly corrupt it to make it noise. And it's very important, okay? Let me highlight this. Very important that this final product is as noisy as possible. Okay, why? Okay, anyone can tell me why the final embedding corruption should be as noisy as possible? Anyone want to guess or infer or something? Not.
I mean,
Okay.
to be honest, I feel that the getting as much noise in as possible as your first step is mainly for robustness and generalization. Because then once you start the denoising process, the model will have, I guess, kind of like how do I explain it? Like more latent avenues to reason from, and then break down in the time step process towards its conditioning variable, towards different end goals or end products. So I feel like if you start with a less noisy image and you train on it repetitively through multiple epochs, I think that would cause the diffusion model or the diffusion transformer, whichever architecture model, to kind of be more limited because its start point is more limited and has like a kind of like a preconceived image within it already, if that makes sense. I'm having a hard time explaining it, but that is my understanding of the diffusion process.
Yeah, essentially what you say is correct. So let me just illustrate this with some images. So imagine you have a sports car image, okay, and then you diffuse it until complete garbage. I'm sorry, not diffuse, you corrupt it until it's complete garbage. And then you have maybe a triangle and you diffuse you corrupt it until this. You have a circle, you corrupt this until this. And maybe you have a square and you corrupt until this. Essentially, all of them, the endpoint of corruption is the same. So what you can do is you can start off with, this enables you to start off with random noise. Any trajectory backwards. Okay, because when you do your training set, you make all of the original images become garbage. You can start from garbage and go back to the images. Okay, assuming that you did not corrupt them fully, and in your training set, your circle maybe you corrupt until maybe something like this. Your square you corrupt until maybe like this, and your triangle you corrupt until like this, and your car maybe you corrupt until like that. You can see that this final corruption that let me just circle this in maybe green color. Yeah, your final corruption for each image, if let's say you don't corrupt it fully, your reverse process, okay, if you give it this random noise here, because it has not been trained to regenerate from random noise back to the original, if it has only been trained to generate from a half corrupted image back to the image itself, you can't really get very reliable generation if you start from complete garbage noise back to the original image. So it's very important that this last part must be pure noise as much as possible, make it as garbage as possible. Then you give yourself the room to start with garbage and get back something nice. Right? So because we are training the reverse process here, it is very important to give all the training samples that are needed to get back from garbage back to the original samples. So this is the key reason why I emphasize that this pure noise is very important in the diffusion process, right? So yeah, I think the intuition is correct. So this is really cool because just from this pure noise, you just condition it with maybe in the stable diffusion sense, you condition it with the text that you want to diffuse to, or you condition it with the image that you want to diffuse to. In this diffusion large language model, you can condition it with the prompt that you give it, as well as the existing mask. So in the diffusion language model, although it's not in the Mercury 2 paper, but if you read the LADA paper, the diffusion paper on LADA, what you condition on is you condition on the input prompt, and then you have your output tokens. Rather, I can put input tokens and output tokens. Okay, the input tokens are essentially unmasked, and the output tokens are masked, and then they gradually become unmasked. So essentially, what you do is you start off with this set of this is your condition, and you slowly try to unmask your output tokens given this condition. So this is the condition, the conditional variable, or the variable that your generation is conditioned on. Okay, it's conditioned on the entire input sequence and the output sequence. It's just that your output sequence is not fully unmasked. You unmask some each step. So essentially, when you do something like this, you help to, you know, basically from a complete garbage output, you slowly unmask bit by bit, and you get a very refined output. Okay, so I know this might be a bit more daunting right now by just words. So now let's take a look at some visuals. All right, so let's take a look at this illustration of an embedding vector. So what's an embedding vector is usually something like, in this case, this is like 0, and this is like over here, the blue color means the bigger the number. So like, sorry, this part in the center should be 1. Okay, if you look at the graph above, this dark blue represents the higher numbers. So this is like 1, and this one here is 0, and this one down here will be -1. So you can represent your embedding vector as n numbers, okay, each between -1 and 1. Okay, it depends whether you want to limit it to -1 and 1, but essentially an embedding vector looks like this. In this case, this embedding vector looks something like this, and then you continue until you reach -1 and so on. So this is your embedding vectors. And this is essentially a series of numbers in a vector, basically a sequence of numbers, and this represents something. Usually an embedding vector, if you were to represent it in a certain space, like you compress down to 2 dimensions, usually you might get the more similar words in the same place. Like for example, you can have man is here, and right next to man, maybe we have boy. So this in embedding space very, very similar. And then maybe at the other end of the embedding space, somewhere at the other side, maybe here, we could have house, because maybe the animate objects are at the top and the inanimate objects are at the bottom. So your embedding vector represents a certain semantic meaning, and what it represents, it really depends on how you train your embedding vectors. And here, let's have an embedding vector that is, totally great. This is my definition of complete clean vectors, where maybe this is your original vector that maybe represents the word man. All right. And now what we want to do is we want to corrupt this vector. We want to add noise to it. I don't know, add Gaussian noise, add whatever noise you want to add to make this vector become corrupt. Okay. And as I said before, why do we want to make it corrupt? The reason is because if we corrupt the embedding back to pure noise, we can do the reverse diffusion process to get back the clean embeddings again. And it's very important to corrupt it until it becomes pure noise so that you have all the pathways back to become clean. So this is an example of a noisy vector. This vector is like the stock market, up, down, up, down, up, down. It's you can't really tell what this vector is. And this is the result of maybe corrupting this many, many times. And now we have the forward diffusion and the reverse diffusion process. So the forward diffusion, okay, so over here, maybe let's not call it forward and reverse because it's confusing. Let's just call this the noising and denoising process. So this Q here is the noising process because you're adding more and more noise to your signal until it becomes complete garbage. And here you have the denoising process. Yeah. So something like this, okay, you could have many, many things. And this, okay, so over here, what we can do is that as you can see the original signal, after you add more and more noise, it becomes like completely garbage. And then if you recover it back, you get back the signal. So Q makes signal become noise, P reverses it. Okay, so essentially Q, let me emphasize this here again. Q is given. Okay, you are the one who creates Q. You decide what noise to add. P is learned. Because after you do the corruption of the noise, you try to predict back the unnoised version. Okay, very, very simple logic, but such a powerful impact. So here is a bit different from this part here. So now, assuming that each part here is an embedding vector. Okay, so earlier on, maybe this is token 1, and down here is token 2, and so on. So apart from like doing the kind of diffusion across the embedding vector itself, what if you can also do it on all across all the tokens in the sequence? And here you can see that uh, these are the confirm tokens. All right, this square means confirm tokens. So we can uniformly unmask, uniformly mask the tokens downwards. So you can see at each step, more and more tokens become white. So white means mask. All right, and in the end, it's completely masked over here. And then if you do the reverse process, you conditionally unmask some tokens every step. So every single line here is a time step. Okay, I didn't explain this just now. As you go back, you can see from a completely masked sequence, you perhaps unmask the most confident token that you predict based on your prediction probabilities. You put back those tokens that are like to you the most confident, like you are very sure that the token is there, and then you slowly go back and get back your original sequence of tokens that are very, very, you are very, very sure that this is the set of tokens because you do this unmasking process many times. And yeah, basically this is the idea of how this diffusion can work on tokens. You can not only do diffusion over like the embedding itself, you can also do the diffusion step to predict which token should be unmasked. Yeah, so these are two separate things. One is you predict the embedding space itself. The second one is you predict the which token should be unmasked. So this is something that is quite unique to the diffusion language models because I don't think this step is there in stable diffusion. Like you don't conditionally predict the patches. Yeah, you predict all at once, right? Here you can conditionally unmask the patches. All right. So I see some comment here. Okay, yeah. All right, that's all. So, okay, this is a little confusing right now because, you might be asking me, why do we need to do this? Like you look at a stable diffusion, right? Is there a mask and unmasked in stable diffusion? Like this is your image, you predict back this one, and then you predict back, sorry, from this you predict to here, and then you predict to here. There's no real masking in image-based diffusion. Then you might be asking me like, why do we mask? Why do we unmask the tokens in a sequence? Like, Why do we do that for text? Yeah, so why can't we just predict the entire text at one go without doing the unmasking and masking? And I mean, that's a question I asked myself also. And actually, I haven't really found the answer in any text. And what I could say is that maybe this kind of selective unmasking helps to train the model a little more reliably because, like, from this step of predicting two more mask tokens here, and if your loss is only based on like which tokens, when the tokens are unmasked, whether they are correct, yeah, maybe you get more reliable prediction as compared to predicting the entire sequence of tokens, which may be wrong. Now you just focus on maybe predicting two more tokens, maybe at each time step. Maybe you get a more reliable loss. So I'm not too sure myself why is there this unmasking and masking in this sequence-based diffusion language model, while there's no such masking and unmasking in a stable diffusion. So one reason might be it's more stable for training. Yeah. So in fact, Lada was one of the first that did it. Based on my understanding of Lada, it's just basically unmasking the tokens each step based on the highest confidence scores of the tokens. Okay, so the tokens with the highest confidence, you unmask it. So maybe with this iterative approach of unmasking, it increases the reliability or the accuracy of the final output. So they must have done some experiments and came up with this methodology. Yeah, I just wonder, whether this would apply to images as well. So these are some questions that I'm still thinking to myself. And if you have the answer, let me know. If not, we continue to find out why this is done, right? But I just want to let you know this is why it's done. All right. At least this is not what is said in the Mercury paper, but based on what you see in the illustration of how it works, it kind of looks like the unmasking is done iteratively as well, right? If you look here, the dark blue means it's unmasked. So, we have to piece together pieces of the puzzle along with some open source papers and, their closed source paper. We try to figure out what they do. It is most definitely an iterative unmasking of the tokens and an iterative refinement of the embedding space of each token. Why? I mean, you look at this, every step, the word changes. I mean, the token here changes, which means that the embedding space of these vectors must be very, very messy. And then eventually it becomes less and less noisy. And eventually it becomes the final token here. So from this illustration alone, it seems very likely that it's following the same process as this paper, simple diffusion language models, where you predict the vector to be less noisy and you also predict the mask to be less. I mean, you unmask it gradually over time as well. So it kind of looks like it's doing this, right? So yeah, I know it has been a handful of explanations and illustrations. Before I move to the math, any questions for this part of the discussion? Or good? Okay, then let's move on to the math. All right, this part is a little daunting, so I hope don't worry, even if you don't understand the math, you understand the diagram, right? So it's essentially explaining this diagram, all right? It's just that the Mercury 2 paper has no diagram, so I have to find my own diagrams for this. So this is the math in the paper. Be prepared for it. So the math actually is quite little because they don't reveal their secret sauce. But you can see that the diffusion is pair of forward and reverse process. And the forward or noising process starts from clean data X, okay, which is like a sequence of tokens. Over here, this signal here, um, this is like a one-dimensional sequence, but if you can treat each data point here as an embedding, then that will make more sense. Like, so maybe, that earlier I mentioned that this whole thing is one embedding, but now we just make sure that, like this white square here is one embedding vector. Then it will make sense. So you corrupt every single embedding vector all the way until you reach garbage. Okay, so actually this is the process of corruption for one single vector. All right, but you imagine you corrupt all the vectors all at one shot. Okay, maybe don't treat data points as embedding. Just treat this X as one token. Okay, so this thing is the vector embedding. Just treat this whole thing as a vector embedding, and we corrupt the vector embedding to make it pure garbage. All right, so what we have here, we have X is a sequence of tokens. Okay, so maybe in line with this explanation, let's just say that this one thing, this one single thing here is a vector embedding. Okay, so it's in line with what we have here in the text. So every single X here, okay, is every single small X, okay, is a sequence of tokens. So this is a sequence of tokens. So this is one token, token one. This is token two. I just put here T2, token two. This is token one, and so on. So essentially, we can basically corrupt this more and more using this thing called ZAC. Right? So ZT is basically the level of corruption. So ZAC1 is the first layer here, where we have corrupted the signal one time. And then after we corrupt the second time, it'll be ZAC2, and so on until we reach like ZT at the bottom, maybe Z big T, okay? Because this is the final corruption of the signal. So we corrupt it using this process, Q, okay, which takes in the previous level of corruption, and then we, corrupt it to the current level of corruption. So these latents represent increasingly noisy versions of X. And the final Z big T, see, this one I labeled wrongly. It should be Z big T. The final Z big T should be the most corrupted um, embedding vectors. And it's very important, as I highlight again, to make sure that the final corrupted embedding, or in this case, the sequence of embeddings, is as noisy as possible. Okay, reasons I've explained many times in this discussion already, because you want to be able to generate back from noise. So the corruption needs to go to noise. All right. So this essentially is given. So I emphasize again, Q is known because you are the one who designed Q. You are the one who designed the corruption. And this P theta is learned. Okay, there's a reason why it's P theta and not Q theta, because there's no theta in Q. Okay, what is theta? Theta is essentially your learnable parameters. Okay, so there's a reason why there's no Q theta in this, but P theta backwards, because the P theta here, you need to learn how to denoise your noise. All right, you need to learn how to reverse the noising process. And this P denoising process takes in the noisy input and comes up with the input that is one level less noisy. All right, one time step less noisy. So you can see the math looks very daunting, but essentially what this shows is that Q makes it more noisy. Look at the TLDR, right? Q makes it more noisy. P makes it more clean. X is your clean data, and Z, whatever T is your noisy data. And ZT is your final noisy data. Z big T is the most noisy version of your data. All right. So any questions here? Because this is quite important. The definitions are quite important because we're going to have a monster of an equation the next slide. Oh, okay. Okay. I think this should be all right, I hope. All right, let's move on to the next slide. Okay, what is this monster of an equation here, right? So this again is in the paper by Mercury, the first version of Mercury. I don't think they changed much for Mercury 2, other than maybe making the data set bigger and maybe refining some of the model, but the loss functions and so on should be about the same. You can see that what you do here is that you have learned parameters theta, and hence you denote by p theta. I see they mentioned the same as what I was saying. Right? The functions, parameters are chosen to minimize a loss that fits P to reverse the effects of the function Q. In effect, this can be learned. This can be achieved by learning a denoising model by minimizing this monster here. All right, and what this means, let's unpack this equation one by one, shall we? All right. So the loss is basically the expectation over time, means um, we predict the noise, the less noisy version, across all versions of noise. All right, all was it across all corruptions of noise, all levels of corruptions. Okay, because like your small t represents the the time. The bigger your t is, the more corrupt your noise. So you want to average out across all the level of noises you added, and you want to see how good it is at predicting your original signal. So, of course, the more corrupt the noise, the harder it is to predict the original signal, right? So this part here, this is a user specified function. We will cover this later. All right. Let's just ignore that for now. This gamma t, let's just throw it out of the window. We just ignore, pretend there's no gamma t. Let's just take a look at this expectation term here. So this expectation term here means that you have zt chosen, okay, from this distribution Q. Okay, what is this Q? As we mentioned in the earlier slide, Q is the noising process. So what this complicated expectation means is that take any level of noise zt. Okay, take any level of noise zt. Okay, because we expect over all time already, right? So can we predict x given any level of noise zt? Can we reverse the diffusion process to predict x? And basically, how close your x is. Let's take a look at this final term here, log p theta. Okay, for those experts in math, can you tell me what is log 1? Anyone? This is a math question. What's the answer for log 1? Okay, I'll yes, Derek?
I'll be honest, I forgot.
Okay, answer is 0. Okay, because log is like e to the power of any number to the power of 0 is 1. Like e to the power of 0 is 1. So log 1 gives you 0 because you get back the power, right? Yeah. So what this means is that if my p theta x given zt, if my px given zt is the same as 1, then my log term is 0, and then my loss will be 0 because, anything times 0 is 0. So essentially, if x is exactly, uh, if my probability of, if x is exactly as predicted, then, p theta of x given zt will be equals to 1 because, for that, okay, x itself has many different, like there's many different values you can take. So this over here, you do the expectations over this thing here. This actually cross entropy. So if you expand out this term here, you will get something like, uh, okay, it's a bit hard to, but the idea is you need to be able to predict exactly what this x is based on your based on your original x, and then this probability term here will be 1. Okay, and when this probability term is 1, then it'll be 0. Okay, so this basically means that uh, if I can predict exactly as intended, then my loss term will be 0. But if I cannot predict exactly as intended, so when it's supposed to be this x, I predict something else, then your log term will be a number that is greater than 0. So there will be some loss, and you will have a negative loss term. So essentially, if you cannot recover, okay, so the idea here is, this is the standard cross entropy equation. So if I'm not wrong, this is cross entropy. Yeah, you can go and search it up. Yeah. So if you cannot predict this term properly, it means that you cannot reconstruct x, in other words. Okay, of course, you can do other kinds of laws, like maybe mean square error loss or something. There are different ways to do loss, but cross entropy has been quite like the bread and butter of machine learning. So essentially, this is what we do to do reconstruction. And yeah, you can use different kinds of loss function. The idea is that if you can predict back your original data x, then you should not penalize the model. But if you cannot predict your data x, then you should penalize the model. So essentially, this is the kind of loss that we try to learn. All right. So this is essentially what is going on here. And I think this is something that is quite quite cool because you just by using something like this, just by trying to predict back the noise to make it such that it's you know you can predict it. This is the crux of diffusion models. Like you just need to learn how to predict back the less noisy version of your data given your noise. Okay, over here they have an extra term. Let's bring back that gamma term that we skipped out just now. This gamma term is a specified function that assigns a weight to each noise level, right? And what this does is that you can then say that, hey, maybe at the I want to penalize the lower noise levels more because the noise levels is very, very close to the final image already. I want to make sure that it can generate better. So if you penalize it more, you get more fine details that are constructed because you make sure that the model focuses better on the last mile. Right? If you penalize the high noise more, then it can give you like a global reconstruction because from very, very messy data, I can give you back the structure, the backbone, maybe like can come back the paragraphs and so on. Because I penalize the high noise reconstruction more, maybe I can get better reconstruction. So I'm not sure what's their schedule like for this function. Maybe they start by training the high level global construction first, then they train the fine details. You could do this loss function with a different gamma t at each training cycle. You could do that. And I would say that it makes more sense to train global first, then go down to the specifics so that your model has a better global view before you go to specifics. Or it could be the other way around. It could be maybe you train the specifics more, then you go back to the global level. I'm not sure what works better, but the idea is you can vary this function here and you can train your loss function, train your model to better predict either the fine details or the global details, right? And over here, we can see that there's some probability terms you can use here um, to basically get back a less noisy version of your data. So you can use this for generation by saying that okay, after we do our predictor here, we can then generate back our noisy version, our one step less noisy version by putting in this p that we have learned here iteratively, okay, to get back this one here. Yeah, so the exact math of here I'm not going to go through, but the idea is once you have learned how to get this p theta, you can use it to generate images. What this equation is just trying to, or use it to generate back your original vectors. What this equation here is just trying to say that. Okay, any questions for this? This is probably the hardest slide in the entire presentation. So in fact, when I look at this equation here, I also like was a bit confused by I went to find out what exactly each term means. So hopefully this makes sense to you. Okay, I'll move on. Okay, so the architecture wise, they openly admit that they use the transformer architecture, and I think that's a good thing because transformer architectures have shown to be very versatile. And in fact, if you look at the diffusion transformers, like this paper called Scalable Diffusion Models with Transformers, if they just replace the UNet with a transformer module, they actually showed that the generation is way better. So transformer architectures are still very useful. Yeah. So they use the transformer architecture, and the difference is that instead of doing next token prediction, they do this monster of a loss function to predict back the original input given various levels of corruption. So this is exactly what they're doing. And um, they also mentioned you can use UNet and so on, but they have opted to use a transformer architecture. Just take note. Okay. So they also say that this helps them benefit from advances of transformers as well. Simplifies hyperparameter search because people have already done that. We have already great models of transformers, and you can just use those models. Just change your loss function and also change your training samples. Okay, I haven't talked about training samples yet, but later I'll touch a bit on it. So you can also use various known techniques like RLHF, direct preference optimization to help to improve performance. In fact, recently there's like stuff like GRPO and so on, more different POs, like different policy optimizations or preference optimizations. You can use this kind of fine-tuning strategies to learn a diffusion transformer as well. Okay, it's not like it doesn't mean that just because it's a diffusion transformer, you cannot use any of this, because as long as you have your input prompts and your output tokens, you can essentially use the same methods as transformer training. Okay, later I'll tell you how exactly I think they did the training. How do we get the input output pairs? Later I'll try to explain a bit. Okay. So over here we have tokens of 32,768 tokens, much like the original ChatGPT, but they can supplement up to 1 to 8,000 tokens. Right. So this is something that is currently a limitation right now, but I think it will expand even more. Okay, I'm quite sure you can expand to 1 million tokens in like less than a year. Yeah, it just depends on how you want to train your models, because the higher your sequence, the likelihood of your diffusion being like the loss becoming much higher is great. So you need to kind of mitigate your loss term because you have too many tokens to predict. So I think you can predict for longer sequences, but you need to have a small robust model first. Then you extend it to bigger and bigger longer and longer sequences. So let me explain a bit on how I think the input and outputs are trained. So let me go back. Okay, which is a good slide to land on. I think maybe we talk about it from this slide here. All right. So you can see that this is the unmasking step for each token. And what happens is that you have your input prompt here. Like, for example, write me a poem about cats. Okay, this is your input prompt. So this is actually, although not shown here, this is actually all in the block of text that is given to the diffusion transformer. So all this here are unmasked. Okay, by the way, whatever I'm talking about here are all speculation, because the Mercury paper did not say how they train it, but I just took some info from the Lada paper and so on, and just pieced together some like how it might be trained. So you have your prompt here that's unmasked, and you have your output tokens here that are initially masked, and then you gradually mask them. Sorry, gradually unmask them. Okay, and usually what you do is that you train this for fixed block size L. So maybe your L could be like, maybe in this case, 32,000 tokens. And you might asking me like, how is it possible to output 32,000 tokens every single time that, you ask a prompt? Because, some prompts have short answers, like what is 1 plus 1? Maybe your answer is 2. Then if you want to ask an essay, then maybe you need um, a longer sequence length. Yeah. I mean, one way is that you have various length outputs here and then you choose the best one, but I think that's a bit too inefficient. What is likely going to happen is that one of these tokens here, if you look at the Lada paper, maybe I'll talk about the Lada paper again another time. You have an end of sequence token, end of sequence. So your original data set should contain some end of sequence tokens here that you predict. So the moment you reach the end of sequence, you stop. All right. So essentially, this helps you to do variable length output using a fixed block of outputs. Because the moment you generate an end of sequence here, and then maybe this could be a poem. The poem is, and then you have end of sequence. So you straight away, although there's still some stuff here, this remaining stuff is random stuff. This doesn't get output to the user, because when you see the end of sequence token, you just cancel this whole thing out, and then this is what is returned to the user. So this is your output prompt. Okay, so this is probably what's happening to get variable length output. And now I talk about training strategies. Okay, how do we use the input output to generate like training sequences? So for example, you could have like, write me a poem about cats, and then like, cats are nice. Maybe this is the poem. All right, they catch mice. All right, maybe the poem is just 2 sentences. So this is like maybe the original input output. And what could be done is that you you corrupt this one here. You corrupt this uniformly to get you your mask tokens. Okay, so maybe Here, the first one could be cats are blank, they blank mice. Okay, this is one, and you could do like masks are nice, masks catch mice. So you could corrupt it many different ways. And you don't just corrupt the masks, you also do some corruption with the tokens also. So you also corrupt the tokens. So corrupt the embedding vectors. So you could make it more and more corrupt. So okay, like one example is here, instead of cats, maybe your corrupted token can become like dogs or something like that. Yeah. So you could corrupt your tokens here, and essentially, uh, this kind of forms the kind of noise. This is your ZT that you are creating here. So you form a noise Z1 maybe, and then you corrupt it even more. You form Z2 and so on. And each corrupted version, you also have a random masking for all this. So essentially, you have many, many. Can you imagine that this one single prompt here, you have many, many different data sets you can get because you mask, okay, not only are the positions masked, so your corruption has two forms. One is mask tokens, and the second form is corrupt the embedding vector for the token. So I believe they do both kind of masking. And from these two kind of masking, you can see that just a simple output like this, you can have like million different possibilities of corrupted noise. And then you can train your decoder from various mask positions to decode back the original output here. Okay, so I have a quick question here. Do you think this is like do you think there's more training data that can be gotten from one single input output prompt compared to an autoregressive model? So autoregressive model, maybe the output you just trying to cats and then you predict R, and then like cats R, you try to predict nice. So this is autoregressive. Which do you think has more samples for training? Okay, do you think this is autoregressive at the top, and this one here is diffusion models, diffusion language models? Anyone want to answer? Like which kind of training strategies has more samples in it? Just from this input output prompt, and then just doing whatever corruption or in the autoregressive terms like predicting the next token. Which do you think has more training examples? Anyone?
Prob Probably diffusion, just because of the way you have more avenues for producing samples to train on. You have multiple ways to take a simple training example and branch out with multiple different corruptions of it over time and create a bunch of different example or training samples from one uh, input of data set example.
Yeah, correct. So I mean, this is something that I think Bird also had an advantage. So for example, you can say the cat set on the mat, right? So in 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 a mask term, you can mask any token. You can mask this one. You can also mask this one, and you can also mask. Yeah. So you can mask a lot of different tokens here, and like all this, you can still use it back to predict back the original sequence. This is very, very free, and you can not just mask one token, you can mask two or three, and you can mask the whole thing. Compared to autoregressive, where you only predict the next token, here there's so many possibilities of what you can predict because you can predict the middle, the left, the right. Yeah, in fact, this is one of the reasons why I kind of like BERT at first before GPT took over. Because BERT, you can do like fill in the blank style thing, so you can get your context from both the front and the back. But for generation, doesn't really make sense to give you the backfill tokens and generate the middle in an autoregressive way because you don't know what tokens will be in the future. But for diffusion, it's okay to generate the future because you can use the future tokens to condition the middle. Yeah. So essentially, I treat diffusion models as an bird on steroids or something, like a super powered bird, because you can use like this kind of mask tokens to give you unlimited training data. Like there's really I think the biggest training issue of diffusion models is there's too much data to train on. I have to ask the people who train it. But I really think that there's a lot of training data because just stable diffusion alone, like from one image you can have millions of samples already, like just by the number of noise and so on. Like you can imagine the number of samples you can have for a diffusion model. Yeah, so this is a huge advantage because I think they are more resilient to noise. Right? Diffusion models will likely be more resilient to noise because they are trained on noise. Like they are trained on so much noise, even you perturb your data a lot, you likely can still get it back. Yeah, so this is something that is quite nice. And yeah, any other questions for
Yeah,
this?
I want to add on this topic also. Like there's more nuance to it in terms of how auto-regressive model is trained. It's it's not necessary. I mean, the community they eventually settled on causal masking, but actually that's not like it's not necessarily the only way to do it. Ite has an article on it. He explained why, like his understanding of why the community eventually settled on all causal masking. But actually, you can do it in a similar way as uh using autoregressive, not BERT, but autoregressive LLM. You can also just mask some token in the middle. It's possible to do that. It just the short answer on why they don't do it is because um cause how attention score is calculated uh during deployment you can't use Kiwi cache, which means the generation is very and training is very expensive. But technically, it is still possible to train to to do non-causal masking as well. Yeah.
Well, that's not just the KV catch on. That was actually the point I was going to bring up. That's not just like the autoregressive transformers. That's just like diffusion in general. I really like it, but I hate the idea that you have one training example you want to train on, and then you have to train like a gajillion epochs just to get your one training example. Like with autoregressive, it's a start to finish. You just take the training example, you do your loss function, and then you can immediately compute it in one epoch. And that's beautiful because then you can grind through training examples by the billions and just like mass produce them. The issue with diffusion is that it's great for limited data sets. So it's very human like, where you can take a small data set to a baby, and the baby will learn it from a bunch of different angles and generalize very robustly from it. It's very human like learning. But the big thing about diffusion is that it's just the training can be so expensive for so little training examples. Each training example is going to eat up so much training epochs because of the inherent nature of all the different ways it breaks down in the masking and noising process. But that was my only big hang up on diffusion, is that if we could find a way to kind of cheat it a little bit, or control it, I think it would have like huge implications for like universal training for all people, or like generalizing training for all groups, because I feel like it's super expensive for the amount of training examples with diffusion in general.
Mm. Well, but the benefit is that you can have very little data and still make the most sense out of it. Yeah,
Yeah, I
and you
don't know
don't.
if
Yeah.
it's I don't know if it's like what do you call it? Like I don't know if it's like a weakness, but more of like a trade-off where you specialize on a few couple of training sets or training examples, and you just get really robust and general on those few examples and get really good generalization out of them. It's really, I mean, it's really more of a change up or trade up than really like a weakness. But I don't know.
It will be good if they release some kind of evaluation study on this. How data efficient is the diffusion approach versus autoregressive approach?
Yeah, yeah, for sure. I think an ablation is needed just so we can have like an objective analysis of just what is really giving the performance.
If it's one of their advantage, then if I were then I would like show something on that. Yeah.
I
Yeah,
mean, it's
I think
possible.
we
Yeah.
can probably find information on some open source papers. Let me go and take a read.
Mm.
I think there should be. I think it will definitely be more sample efficient. based on my understanding of diffusion. It will definitely be more sample efficient.
But there's actually for autoregressive you have a kind of a workaround as well. If you there's a paper released by Stanford, the same group that works on the tiny sorry, not tiny, sorry. There's S1 scaling paper. They basically take the storybook and they just do some kind of data augmentation, like give the say for some space sequence, right? You can, you know, paraphrase it. Like, in a way, you
Mm.
can also generate many different variants from the same data. It's like it's very similar to last time how invasion domain, how do you augment the data by flipping or rotate, add noise. So it's possible to do something similar to text data as well. And they also can screw up text data. Yeah. So yeah, there's a workaround for
You,
auto.
do you know what's the most impressive thing? You can add all those data augmentation strategies you use for autoregressive models, and they can become also the data
Yes, yes,
augmentation
yes.
in
It's not,
diffusion.
it's
Yeah,
complementary. Yeah, I
yeah.
agree. It's complementary.
So
Yes.
actually, diffusion has way more samples than autoregressive. Like all the data augmentation you use for autoregressive, apply the same for diffusion. Plus, some more you can perturb some more with the
Yeah, yeah,
vectors
yeah.
and the
That's
mask.
why it's
So
interesting to see some result on that. Yeah.
so here's the question. So we had a lot of data augmentation in the hierarchical reasoning model. And there's a lot of data augmentation involved in that paper that helped with performance. So my question is, how does that compare to this? Like, is diffusion doing even more data augmentation than the HRM paper, or is it a different type of augmentation?
It definitely is more than the HR because HRM is still autoregressive models. So just by
Yeah,
just by
yeah.
that alone, it is already more data augment. It's already more samples in the data you can have because you have different strategies to corrupt your data. So you already have a lot more samples.
Yeah, we should explore it. That sounds really cool, though. I think we're getting a lot out of the data augmentation. I think it's having an effect on the training process.
Yeah, I just find it very interesting why there's this masking and unmasking happening in the text domain when I don't see it in the image domain. So I'm quite curious whether the modern variants of stable diffusion, they do masking. Because I mean it's kind of weird why it's only exclusive to text domain. But
It could just have to do with like it could just have to do with that the masking adds another layer of augmentation and like almost like noising or corruption to the data. It could be it's almost adding like another flavor to it. So it's allowing for like it's almost like forcing the model to kind of adapt and aggregate like another level of like abstraction or generalizable reasoning based on the data set. Because I think if you just do the noising of the data or of the tokens and then run like a denoising training on it, it may be that it's insufficient because of the I don't want to say the complexity of language, but the grammatical logic of language. Because with pixels, it's really easy, right? You can just Gaussian noise a image of pixels, and then you just denoise it. And you just run a basic like loss function on it. It's really easy actually for most neural networks because it's a very simple task. But I feel because of the complexities of language, you require another layer of like corruption or of augmentation, which is what the masking is. So they kind of just steal masking from the autoregressive field and they just bring it over to diffusion, and it gives the model like almost like another level of like generalization that helps it with better performance. That's my instinct. That's how I feel is what's happening with the masking.
that's very cool. Yeah, maybe I should email the authors of this diffusion language model, see why they did masking. Or Lada actually did masking first, I think.
Yeah, because
Yeah.
now I'm just like I'm coming up with like all of these theories now because I really want to know. It's like what is the masking doing to the training?
Yeah, I think maybe because in text, if you let it diffuse like images like this, you see like images, even if your image becomes a little less noisy, with a little different color, you may not notice it, but for text, maybe you notice it. It can be a very jarring thing if one pixel is totally wrong. So it might be that you condition on already some fixed pixels so that you smooth out the rest of your tokens so that it looks nicer when you already unmask some of them. Yeah, I mean that's one of my theories. Like because in image your pixels can even you have one wrong pixel, it doesn't hurt that much, but it hurts a lot for
Yeah,
text. Yeah.
that's exactly what it is. I mean, as with pixels, it's very easy because it's a very literal. Like all of your work is on the canvas. But with say like text generation, it requires a lot of like latent reasoning in the neural network. Like you can't just like kind of figure out a couple of pixels and then just build out from there. You kind of have to like almost plan it out in the internal structure of the neural network that's doing the denoising. So I feel like adding the masking is kind of like almost a way to add another layer of corruption and data augmentation to add further robustness and generalization to the neural network. And I don't think it matters what it is. I mean, transformers are great. They do everything. They're a do-all neural network, but I feel like I'm sure you could do a study, apply it to any neural network, recurrent, UNet, and I'm sure you're going to get the same improvement results. It's because of the masking and the data augmentation. It's allowing the neural network to generalize much better on the text modality. That's really what I think it is.
Mm, interesting. Yeah. All right. I think that's probably why. I mean, of course we need to find out more. But it's really cool how you can use the noise process and the denoising to generate stuff, and just a simple cross entropy term here to just make sure that whenever your x is supposed to be one, it's one, and when x is zero, to make this loss term zero. Such a simple equation like that can give such great results. It's quite cool. I think it definitely is not without its drawbacks though, because I can imagine that if your sequence length is longer, this might be harder to train. Yeah, because you have to predict a larger patch of larger sequence, and if you predict everything in parallel, um, the latency might increase because you have to do. Okay, it depends how you do your prediction. If you do it one by one sequentially, then your latency will increase. But if you do it all in parallel, then it's okay. Yeah, but I can foresee that if your output token sequence length has increased, there will be more latency needed for this process. But still, I think it's less latency than autoregressive. So it's fine. Yeah, it's fine.
Sorry,
Yeah.
by default it's parallel, right? What do you mean by
Oh, because you see, let's say you have a sequence of data, and then you want to predict using your model, and you have to use a p theta here using some equations to do this. You need to do this equation here. Yeah. So essentially, when you do this over here, uh, yeah, you kind of need to like evaluate every single token at the same time.
yeah.
Eh,
So it's in parallel.
Let me think about it. Let me think about it.
The the, the sequential is temporal wise is sequential, right?
Oh, that's true. That's true. When you predict this X here, it's actually predicting the whole sequence. So yeah, actually, you're right. Yeah, that was I was thinking more in terms of you need to run this equation per token, and then it depends on whether this thing is fast or not. But I realized that actually if this is like a vector kind of thing, you can also do the whole thing for all
Yeah,
tokens.
it's a
Yeah.
vector, right? It's a
Yeah.
vector of the whole sequence.
Then okay, then ignore that point. Yeah. So this is an advantage for diffusion models. Then they can do parallel prediction, and then the latency shouldn't shouldn't increase as much for increasing token length for output length. Oh, interesting. Now, I was having this mindset that as we increase the amount of prediction, maybe this equation here will take longer to run, but I don't think so. Yeah, I don't think so. Yeah, looks to me like it's a straightforward probability multiplication kind of thing. It's a vector multiplication, which shouldn't take too much of a time. Yeah. All right, so let's go to questions to ponder. So first question is, how do we know whether the diffusion approaches know the number of tokens to output? I believe they use an end of sequence token. So this one you can look at the Lada paper. I think maybe I'll talk about the Lada paper next week or something. Yeah, so they incorporate end of sequence to tell the model when to truncate output tokens. Okay, and this is a very interesting strategy because although you still predict the whole batch of tokens at the same time, you know where to stop. All right, so this is what I think happens. Okay, next one. is it more sample efficient than a transformer? And I would say that yes, because you can get more training samples from various masking and corruption of the embedding vectors. Yeah, so essentially from one sample, you can have many, many training samples. Just from one input output pair, you can have many training samples. So, and you can also use the same techniques, can also use same techniques for autoregressive models, uh, can use same data augmentation techniques for diffusion language models. So you get the best of both worlds. Yeah, so you want to say something?
Oh yeah. So first question, I don't understand how do they. You said okay, it's by incorporating end of sequence token, but how does it decide where to put it?
So in the training sample itself, you have to put end of sequence at the end of the sequencer. So like for example, what is 1 plus 1? So this is your input prompt. So maybe this is your input. And then your output would be 2. Yeah, then maybe mass. Yeah, you could have the output sequence, just have an end of sequence token for every single input output pair.
But
Yeah.
but is it possible that at different run, different t during the diffusion process,
Mm,
the
mm,
position of EOS token it can still change, right? Is it possible?
the position, yeah, I think so. Yeah, so if you allow for remasking, you can remask your end of sequence token and then put it somewhere else. Yeah,
No, no, it's not put somewhere. It's generated by the model, right? The
yeah,
EOS is also generated by the model. So
yes, yes, I believe
at
so.
different timestamp, it is possible that this EOS token is moving around, right?
No, no, I don't think so.
You
Like,
are
I think,
you
I
are
think,
saying the at different t, the total max sequence length is fixed.
yeah. So let's go back to that diagram again. So what I'm saying is that, I mean, based on my understanding of the Lada paper, what I'm saying is that one of these values here might be end of sequence. And then once it's unmasked and then given an end of sequence, if this continues all the way to the final output, then we will only show this part of the sequence.
Yeah,
Because here,
so what is the x and y axis?
okay, so over here, this X is all the tokens. So for example, this is like the cat set on the mat and so on. So each of this here is one token. This is the denoising, this is the noising process, and this is the denoising process. So this starts off from like um totally masked. Oops, sorry, let's go back. Fully masked and fully corrupted data. And then you slowly go back until you unmask more and more, and then this is fully unmasked,
Hmm.
uncorrupted.
Is it possible at different position there can be more than one US token at certain t at different position?
I think so. I think so. I mean, you could have
And
other
you
EOS over here also,
then
but
you
you only
find
take you only take the first one.
but during in the vertical line you draw the EOS one, is it possible at certain t the EOS becomes some other token? It's possible, right?
Yes, yes. So
Okay.
when you do remasking in some diffusion models, you allow for remasking. This part here can become a mask at the end. In sometimes that if your token confidence score is quite low after a while, you might want to mask it, and then the EOS might go to somewhere else, and then
Okay,
you
so
yeah.
that means during the diffusion process, the if you find the one the first because the first position of the first US token can vary, that means during the diffusion process, the token length also varies, right?
Your token length is the same for the entire diffusion process. You're still doing the whole block. It's just that at the end of the block
Okay,
where
I see.
yeah,
That's the max. That's a hard limit on this. I see.
it's something like ask you to generate a sequence of text, but anywhere inside you can have one or more EOS.
Okay.
The moment I see EOS, I'm just going to cut off the rest of
Okay.
the block.
I see. I see. Okay.
Yeah.
Got it.
So at least this is not in the Mercury paper, but this something like this is in the Lada paper. So I just
Hmm.
kind of inferred that it should be like that because if not, how are you going to get a variable length output, right? You're not going to be having like 1 to 100,000 tokens and you generate all of them and then see which is better. I don't think that works like that. I still think the end of sequence token is more productionally viable.
Okay.
Wait,
Yeah,
so when it does the end of sequence, is that triggered by like a rule, or is that
it's a
does the
rule.
model learn?
It's a rule. The model will learn because I think all your training input output samples will contain this end of sequence token in the output sample. So you will learn like
Hmm.
how how long should I output based on my input output pairs.
It'll learn, but like it's bound to be wrong, like unless it learns it from the diffusion training loss over time, or
Yeah, it probably learns from the diffusion training loss where the original EOS is. So it
okay.
becomes quite better and better at predicting the correct EOS token.
Yeah, because I feel like you would have to start off with like a rule trigger because it's going to be all over the place. I feel like you just start with like a rule-based trigger and then eventually it'll learn it. I don't know.
Oh, you mean learning the tokens with I don't think it starts off with a rule-based trigger. When I said rule-based, what I'm talking about is that you take the final sequence uh of unmasked and uncorrupted um word embeddings of or tokens, and you just by a rule, if you decode it to be end of sequence, you just truncate. You just if when 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 at inference time, if you see an EOS token, then discard the remaining tokens. Yeah.
Okay,
This
okay.
this was what I meant by rule. So if you're talking about training rule to make sure that your EOS must always be at this position, I don't know. It might be helpful at the beginning, but I still think you should let the model learn on its own because you can't spoon feed the length. You don't know the length. Yeah, you don't know the length of the unless you confirm plus chop knows like MCQ, then your length is always one. Then yeah, by all means you can spoon feed the EOS as the second token. But other than that,
Yeah, I don't feel like it really matters because the model is eventually going to learn how to get EOS right every time, the end of sequence every time, and then start learning like the other stuff. So I don't think it really matters. Like either way, it's going to figure it out. I think it's a nuance at most.
yeah. I really think it's learned by itself. I don't think you spoon feed the end of sequence for these models. Okay. Yeah, if not, I think we are good. So, any other questions on this? Yeah. So really cool. Yeah. So actually, after my discussion with Sergey, I realized that this term doesn't scale up much when your X increases in sequence length. It's probably going to be about the same runtime, or slightly more, which is really cool because uh, this means that it will outspeed and autoregressive models even at larger sequence lengths. So there must be some drawbacks, right? I mean, I'm just thinking about it. There must be some drawbacks to diffusion models. Maybe you can talk a bit of the drawbacks that we can imagine. But let's talk about the last question first. How can we diffuse multimodal embedding tokens? So this is a question that I've been thinking to myself. Like, sure, diffusion works for images, for audio, for text, What if we combine all the modalities together, like what the current large language models can do? There are multimodal language models. You can generate images, audio, text, and so on. Like Gemini is a natively multimodal. So what I'm thinking is that, when you do multimodal kind of data, you still have embedding vectors. So this is like maybe your embedding vectors for one token, and this is embedding vector for another token, and so on. The difference is that maybe in each token here, at the start of the token, you could have an identifier. Like maybe one of the few vectors in there could be the identifier to tell you whether is it like image or this one could be text. And then based on your identifier, you could then send this token so this will be decoded as text token. And this one here might be decoded as images. So I think that it's possible to have multimodal embedding tokens, but your embedding space, part of the embedding space needs to have an identifier tag so that you know how to decode it. Yeah, so based on how you decode that tag, maybe the first two or three vectors, I don't know. I mean, there are different ways to do it. Yeah, maybe the first vector you do a classification kind of thing, Like if the number is 0 to 0.2 is text, 0.2 to 0.6 is image, 0.6 to 1 is video, something like that. Yeah. So or audio. Yeah. So I think as long as you have a way to inside the embedding space itself, identify how to decode it, you are good to go. Then you can decode the multimodal stuff accordingly. So I think that should be possible because with enough training data, you will learn how to do the text as well. Yeah, so machine learning is always like that. You give it enough data, it will learn how to categorize, how to do the kind of distribution that you gave it. You try to replicate the input distribution in the distribution of your samples. It tries to replicate it when you give it new samples or new inputs. So I believe it's entirely possible to put the information inside the embedding itself. Yeah. So that's one way. The other way is, of course, you have different models to do different embeddings um, for for image, audio, and text. But then that means you cannot, put all together. Yeah, so I quite like this decoder thing. I think Gemini released a paper on something like this, multimodal embedding strategy, where in the embedding itself contains the tag for how to decode it. I think it's in one of their robotics papers. Can't remember which paper it is, but I believe this is entirely possible to do so. Yeah. Any other suggestions? Like, how do you think we can diffuse the embedding space and still know how to decode it for different modalities? Okay.
So I don't quite get what's the technical challenge here.
The technical challenge is that usually we only do diffusion of one domain at a time.
Mm.
Yeah. Now we want to do multi-domain input, multi-domain output.
But if they share the same embedding space, why would that be difficult?
Oh, I mean, even you have, like, let's say this is token one, and this is token two, token three, how do you know how to represent them? Like, do you represent them as a text, audio, or image? Just the tokens alone doesn't give you any indication. They're all vectors, you see. How do you know this one I need to use a text decoder? How do you know I need to use an audio decoder and so on?
I see.
Yeah.
I mean, you can always tag them. You can always put different parts of the sequence of tokens. Well, it's not really sequential, but it's a sequence of tokens. You can always put tags at different parts of it that will denote like this starts the audio embeddings, and then you get onto like the video and then, or sorry,
Oh,
the images and the text. You could just put tags on all of them, and then those tags will stay during the decoding process.
oh, that's
Because I
interesting.
thought I
Mm,
thought I thought that's how we were already doing them. I thought we were tagging the multimodals, the multimodality input. I thought we were just tagging all of them.
Interesting. Yeah, I didn't think of this way. So it's something like a HTML tag. You can wrap the image in text, and then you can continue with like this is text, and then you can tag the tokens as well.
I mean, it is like Joe, you said, like with like large autoregressive models, like you can just feed them an like ungodly amount of data, and they figure it all out by themselves. That's easy with multimodality. I think it's with diffusion models, it's tricky because they have such a low sample size because of the nature of their training. Like they're going to be doing a lot of training at a very small uh, data set in order to keep it like practical for training purposes. So I think the only reason you would need to do like tags for the embedding input would be for that use case, is because you have so little data, the model, or maybe I'm wrong. Like, what did the do you think the model would still generalize because of how much sample training it's doing, or how much data augmentation it's doing with the training? Wouldn't it still generalize on such a small data set of multimodal or multimodality?
It's hard to say, like even if you just do
Yeah.
text alone, just the data set alone, you may not tell whether it
Wait,
generalizes until you
wait,
test
wait,
it out.
sorry. They did not even disclose how many tokens the model are trained on.
You mean for
Yeah.
Mercury, is it?
Yeah, Mercury too.
No, no, the data set is not given.
No, I'm not
Oh,
like usually they don't tell you the data set, but they will tell you how many tokens, the number of tokens.
yeah. That's a
I
good
mean,
point.
the only thing that we have is this thing here about the context length of up to 32768
That
tokens.
is that is so little information to work on.
Yeah. I mean, 32,000 and then like up to 128, it's pretty typical of like a corporation sized models. I imagine it's like couple. It might be. What do we think? Like up to a trillion, or just up in the billions? I don't know.
Yeah,
It could be tri
I just realized this is context length, so it may not be the output length is not mentioned also. So I had an impression that this was the output length, but that means the output length itself, we don't know how much it is trained on. Like, yeah, but I don't think it's trained on a huge length of output because when you do your diffusion, like when you do your denoising process, you have a lot of possible data that you can have for longer output. So I think the output is probably short when they
Yeah.
train this.
So apparently on their technical report, I think for Mercury 1, they just said it's overall the model is trained on order of trillions of tokens. That's all the information we have.
And the trillions of tokens might be the same sample corrupted different ways.
So it doesn't specify if it's like training samples or if it's just like original tokens. They just say tokens. Okay.
They say tokens. They just say
Interesting.
yeah.
No, because it's a
Maybe,
lot. It's leaving a lot to imagination. We're just kind of like guessing because
yeah,
it could be all of the above.
I do think it's quite standard nowadays to have trillions of tokens to train even for autoregressive models.
No, I think it's pretty common.
Yeah,
It's pretty
it's quite
common.
standard. It's quite standard
Yeah.
for large scale training to be this amount of tokens.
Even for small model.
Yeah.
Yeah,
So
because you're going to increase the quality just based on increasing the data amount. So here's my opinion. I think what they did is they had enough hardware to kind of train on a large data set of text corpus, and that is also helping a lot with the performance because with diffusion models, they're really cheap at runtime, but they're really expensive at train time.
I think
So
so.
I
Yes.
so I think what they did is they kind of just spent money on the hardware, and they just trained like in a obscene amount of data augmentation on very large data set. I think most corporations aren't going to have that issue with like multimodality. Like they're just going to train on the previously archived data sets that are like trillions of data of tokens, and they're just going to spend all of that hardware on training. And the diffusion model is going to have extremely good performance on multimodal inference. So I don't think it actually matters for corporations. I do think for very small parameter models or very small data sets, I think tagging is a really good idea because it does give the model some guidelines to go off of to kind of jump into like the training process. But that's just an opinion. I really don't know how the fusion would perform.
Yeah. Okay, one of my issues with doing this tag-based token approach is that in diffusion models, sometimes your token doesn't get in the right position. So what if like this one comes here and then you forget to close your image tag and this whole sequence is corrupted. Yeah. So
Yeah, but that's not really a big deal because the diffusion model is going to learn to do that with the training loss anyway. It's the same way it's learning the end of sequence. It would still learn to do that too, wouldn't
hmm,
it?
that's true. That's true. Yeah,
Yeah.
so I cannot say for certainty which approach is better. Certainly, if you use this tagging method, the tagging method would be easier to train, I think, because uh, you can probably use some embeddings from other models because your tokens here still mean the same thing. But if you were to use if you modify the embedding to incorporate modality, then you probably have to train from scratch because I don't think most models do this inside the embedding itself to say whether which modality is. Yeah. So there's some trade-off here. I think this embedding inside the modality itself might be something that sorry, the modality inside the embedding itself might be something that might be better in the long run because then you don't have to do the tokens for image and text. I don't know. Yeah. Do you know how the Gemini multimodal embedding is done? I don't think they release any paper on it.
You
Yeah.
can go ask ET.
Yeah.
I I
Yeah.
wouldn't. I haven't read the Gemini papers, so I wish I could say. I don't even know if they would disclose that.
Yeah. I mean, let's leave it as that. I mean, the rest are speculation already, but I think both methods are probably okay. Yeah, probably if you do it by the tagging method, um, I don't know, you might have more expression for your tokens itself because you have more space compared to taking up some space in the embeddings for your identifier tag. I mean, but the embedding space is quite big, so I don't think it matters that much. Yeah. Okay. I mean, I wouldn't really know. Yeah, this is just speculation right now. But both approaches should still work because the diffusion model will just learn the way the embedding is represented. It will also learn how the sequence is represented and so on. In fact, actually, a diffusion model might be better to do some form of how do you call that? Like it might be better to learn from a wider diverse form of data because when you do the diffusion you do the denoising process, it can actually take into account the full context. So okay, let me just illustrate this in a picture. So I think, let's say, compared to autoregressive models, like you have these few tokens and then you predict your next one. So maybe you have, okay, just use the cat set on the mat again, and then you predict mat. But if you do like the kind of when you do something like this in the diffusion model, you kind of are able to, for example, this part here in an autoregressive model, you don't have the information of whatever's after this mask, right? But here you can use this to infer. So in terms of like you're able to take into account the entire context, front and back, when decoding for diffusion model. So in some sense, I think it might be more beneficial for multimodality to have a like greater idea of what the images,
Yeah,
text
yeah,
represent.
I get what you're saying. Yes, because it's not natural if you use like tokenize the image and just to predict the next patch. Like it's not natural for image.
Yeah, in fact, I think this diffusion thing, if you do it in a diffusion transformer, you might be able to do stable diffusion without the need for stable diffusion elsewhere. You can just do stable
Have you
diffusion.
just I don't know if it's a set but have you guys try out Seedance 2.0? They did not release the technical report, but based off of their previous generation, they do use like a diffusion architecture. Yeah.
Sorry, can you say that again? What 2.0?
Seedance.
How to spell that? Seed dance or seed dance. Okay.
Yeah. So but it's by far the best image, no, not image, like Omni model gener. It's just it's not even close. Like, yeah. But my point is like they given that the previous generation the architecture is also diffusion based. So I think the current version won't be too far off the architecture in terms of architecture design. Yeah. So
I mean,
all this to say that yeah, no, I mean diffusion is much natural for it, be it image or video. A video may not be because temporal wise you're also predicting the future. So maybe autoregressive still fit into that paradigm. But if you want to predict patch by patch within the same frame, then definitely diffusion is much natural choice.
Well,
mhm.
for me, diffusion and autoregressive are both frameworks of prediction. I think it's just different approaches to the same predictive problem. The problem of like doing the next step prediction or whatever. Because I think with autoregressive, you're predicting the next token within the generation, and I think with diffusion, the prediction is happening in time steps. So it's still doing like step by step prediction. It's just doing it differently. But I still think diffusion is
But
much more.
for every time frame you can predict the entire picture, right?
Yeah, so that's my point. I think it's much more natural. I think
That's what I'm
diffusion is
saying.
a
Yes. Yeah. I'm yeah. I agree on the point.
Yeah. Actually,
yes.
the diffusion process is much like writing a book. At first, you come up with a draft, then you refine your draft, add more paragraphs, refine the paragraphs, edit some paragraphs, and so on. While autoregressive model is like writing a book, but you cannot correct what you wrote earlier. Yeah, so so there's definitely some benefit to diffusion in the sense that you can do some error correcting and overall the whole tone would sound more uniform. Like because sometimes for autoregressive models at the start maybe sound very formal, then when you hit a certain word then or token it suddenly spews out lots of garbage or like there's a famous GPT case that you give it seahorses and then it recursively generates and it doesn't stop. Yeah, so stuff like this can be probably solved with diffusion because you are able to see that, hey, how come I'm recursing so much here? Let's stop it. Yeah. So yeah, I mean there's definitely some benefits for diffusion here.
Now, another thing to know, the reason autoregressive took off is because of how easy it was to optimize. It was very easy to work with and to optimize it on NVIDIA hardware stacks and software stacks like CUDA. That's why it has so much speed up on the hardware. But I think diffusion is really untapped because it is definitely harder to optimize. I think like it has a lot of advantages because of the way it computates on general processing hardware. But I think a lot of this potential is untapped because it's not fully optimized. I think there's a lot of optimizations that can be done with the diffusion process on hardware. I think it's really untapped because autoregressive was just happened to be easier to get performance out of. I think that's what happened too.
Mm, yep, definitely. So I think there will be a paradigm shift. My bet is that all models will be diffusion in the near future, and we'll have lots of speed ups. But actually, can you think of some disadvantages? Okay, let's just use the last 1 to 2 minutes to think of some disadvantages of diffusion models because I don't think it can be like all great. There must be some inherent drawbacks here that prevents it from like wide scale adoption. And I let me just start with one drawback. I think, all right, the drawback is that if you have this noise here and then you predict wrongly one of the tokens here, um, or many tokens here you might be like it depends on how robust you are to correct these tokens. You might actually have a stretch of a bad sequence of tokens because of 1 to 2 incorrectly predicted tokens. Because like overall you try to match the entire output, right? So if you have just unfortunately messed up the prediction of a few tokens here, your I mean it may not be very plausible like what's there. Like you might miss out. Or you might feel like, okay, maybe it has like it predicts a source over here. Like let's say if you are talking about like maybe deep research, it maybe it caters 5 tokens for the source, but maybe it turns out you need 7 source citation, and then it turns out you need 7, then like how to shift the remaining tokens to cater for the space needed. Yeah, so I think it might run into problems like that because when you do block prediction like that, and you not necessarily predict from the left to right, sometimes you cater insufficient space for certain things, and then you might.
But
Yeah,
isn't I thought that's exactly its upside, right? Because for the next t step t plus one, it can just change the entire sequence just to cater for that. Basically, can shift all the subsequent token by just to the right, then give you some space because it can always self-correct itself.
I think it's easier said than done because usually the remasking process is based on some prediction probabilities, probably like how confident you are of the prediction. In order to change the entire sequence to the right, you need to change all of the existing tokens to mask, and then after that, in a subsequent step, unmask it. So it's not a one-step process. Like, yeah, it's quite possible that you will have some errors when you shift the whole block to the right.
But it still can use the subsequent t steps to just self-correct.
Probably.
Because that's why I thought is the main advantage over autoregressive, where after you generate, you cannot change. It's fixed.
Yeah, I mean, I'm not sure how robust it is to shift the entire sequence to the right once it realizes it needs more space. I'm not too
Have
sure
you
about that.
have you run some tests like you can take some snapshots of when you do some testing, then can you see like there's this kind of shifting pattern emerge from during the generation process.
I mean, I
Not sure.
went to run the Mercury 2 with the diffusion mode on,
Yeah,
and
yeah.
what I saw is that like even the paragraph starting tokens are not fixed. It's only towards the end then you see it there.
Yeah, so means they can shape.
No, but it comes out as like total noise. It's like not the whole sentence shift to the right kind of thing. It's more like slowly the different parts get filled in, and then eventually it gives you whatever you need. So it means that if you fill in wrongly, the model might just compensate by truncating certain sources or like just, you know,
That
pretending it
that
doesn't.
that sounds very, very bad. If that's the case, then I don't see the
I'm
diffusion.
not too sure. I have to try out more, but so far I gave it text and asked it to replicate the text. It managed to do so quite well. But I haven't really tried it for deep research kind of stuff. I'm intending to try it out. So
I think
yeah.
the kind of thing you can test on is that's actually my current concern of like in terms of limitation. How does it can it scale well in terms of the inference time scaling? Because that's currently where um the 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 breakthrough are, like especially for harder tasks, right? You really need inference your whatever paradigm you're using, you should be able to make use of inference time scaling. If it can't, it's probably very capped by the in terms of what kind of how difficult the task you can give to it to be able to solve it. And I thought like actually my based on my understanding, I feel like diffusion based is already very naturally imbued the inference time scaling with it because the diffusion process itself you can think of is inference time scaling, right? In terms of T steps.
I mean, you have a fixed T steps, so you won't take more than T steps to
Uh,
diffuse backwards.
why you have to fix the T?
Mm, true. You can keep diffusing until your model is
Yeah,
competent.
yeah, yeah, yeah.
Well, that's maybe, but there actually is. I do think there is a point to fixing the T time steps because if you don't fix T time steps, the model's not going to be limited in the amount of time steps it takes to generate the final result. And I think that's going to result in a. It may result in like very inefficient generation, or possibly the model kind of like running into like what is it like overfixation issues or what's the word runoff. It's going to end up running to like runoffs during its rollouts during the inference time or the inference processing.
But it's the
So I
same
do.
for I think it's the same for autoregressive where you want to allocate more time for inference for harder tasks, right?
Yeah, there is that. Yeah, but I feel like with like the diffusion, like with autoregressive, it learns like the step by step prediction, right? So if you let it continue to generate beyond like the limits or the context limits or whatever, I think it'll continue to like generate without like any hiccups because it's just running the same process over and over again. But like with diffusion, I feel like it's more interconnected. So like the time steps all have like a relation to each other, right? Like you can't just like keep generating like ad infinitum and get like a different result or like a supposedly improved result because I think like as you keep generating the time steps, you're eventually gonna like run out of room to like keep making changes to like the embedding space or whatever space you're using for
Mm,
the diffusion process. I think you're gonna eventually gonna run out of like combinatorials for like what you can move around within that space. So, and I could be wrong. I could lack an understanding of how it works, but I think I think there's potential to let it run on forever. But I think like there has to be a way to constrain how it's generating T time steps. Because then otherwise, I feel like it's going to be unrestrained and it's just going to be kind of like going all over the place or end up in loops or whatever.
mm,
You do kind of have that issue with like recursive models where they end up, they do have like that issue where they end up in loops. So you have to do a lot to like normalize them and kind of like constrain their looping process because you do get stuck in loops pretty easily with like recursive models, especially with like, I know like recursive transformers and stuff like that. So I think it depends because it's still like transformer block, but it's diffusion based. So maybe you don't have the same issue, but I don't know. because I feel like diffusion still has like 2 time steps that you're dealing with for the denoising process.
I think usually the diffusion denoising process, especially for this diffusion language models, they have a fixed proportion of tokens they want to unmask each time step. So essentially, if you want to remask back again, it might be difficult because of the way the inference is done. But of course, you can change the way you unmask and remask, but it will take a longer time. Yeah. So I think all these are things that we don't fully understand yet. It's still quite a new field for this. And I mean, who knows? Maybe they have a shift operator in the future where they can shift the entire tokens to the right. I mean, that could be inbuilt in the inference process as well. When you think that, hey, we need more space, then just cater the space without shifting all the rest of the blocks. I think that might be possible. Yeah. But I haven't really seen it done yet, so I have to go read more papers to find out more. But I think this would be something that might affect the the denoising process quite significantly, especially if you already unmask the tokens and it doesn't really it's very hard to mask it back and change it. Yeah. So
But when I test out the Mercury model,
mm,
I see it even after it generates some words, it still can be updated.
yeah, it can be updated. Yeah.
So
It's
why you need the unmask remask thing? Like it's just keep updating, right?
oh no 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 no. So when you see the word keep updating, it means it's not the final form. But if you look at this illustration here, you see those in dark blue are the final forms already. So if let's say my jump is in the wrong position here, I want to shift the jump like 2 positions to the right.
Uh-huh.
I need to remask this jump here, and then I need to unmask this word as jumps.
Sorry, I didn't catch that part. How do we decide which tokens are already finalized?
So they didn't release um they didn't release how they did it, but based on how the LADA paper did it, I'll cover LADA next week likely, is that they based on the confidence scores, basically how high is your probability for that token.
Yeah.
And then
Okay, I can see if they have a higher confidence, then if you have a lower probability of being updated, but you can't just fix it, like just fix it and there's no chance for it to update further because
yeah, yeah,
without the whole sequence, how can you say that token is confirmed correct, right?
correct. There's a chance to update, but that chance
Yeah.
is that means you need to remask it and then unmask it. You cannot just change this word to something else. Like so, you see over here they didn't show the remasking, but once it's unmasked already, it's kind of fixed. So you can see that the whole thing eventually from a light from light
I
background.
feel this is more like in physics there's an annealing process is very similar to that. So when you are already reaching like you let's say it's something it feels like some token if it doesn't change it's like stuck in your local minimum and that's why it just relatively stable. But there's still some chance for it to escape that local minimum and being updated. I think that's
There's a chance. There's a
yeah.
chance. Yes.
Yeah, so I feel the diffusion thing is very I need to read up more on that, but it feels like works in very similar way as annealing. Yeah.
Mm.
So
Maybe
there's
maybe.
still a chance of being updated. And I think it would be good if it's possible to just insert a new token somehow in
Yeah, yeah,
any
yeah.
arbitrary.
Insert
Yes,
or shift the
yes, yes,
tokens. Yeah, then
yes, yes,
you don't have to remask and unmask again. You
yes,
can just
yes,
shift it.
yes, yes.
Actually, maybe they already do that. Yeah, maybe they already do that. Yeah, it's just not released in the paper. Yeah.
And my last comment is like I feel like diffusion what another advantage over autoregressive is once the model realize like in autoregressive like the aha moment right in the inference time scaling aha moment it's like it realized its previous generated sequence are all wrong then you start over again it's like waste of token but here you don't need it once you realize it's wrong you just re-update the token right you do not need to have unnecessary long sequence.
Yeah. Yeah,
Yeah.
that's an advantage for diffusion models.
Yeah.
Yeah. Cool. Any last comments or words before we end today's session?
Nope, just my last comment and then we can end. But honestly, I do think the biggest ultimate weakness of diffusion, I really do think is the training time. I do think that the generalization is amazing, but that generalization is because of the amount of data augmentation and training samples you are extracting out of the data set, the small data set. So you're doing a very, very large amount of training epochs per training example, which can make it very time consuming or very resource consuming. Because I'm sure you could trade off for both. You could just do hardware to speed up the training, but it's very, very resource consuming to train per data set per training example. And I think diffusion needs its fast attention moment, like that kind of aha moment where you get like fast, maybe like fast diffusion or something that allows you to work around that issue and get like a huge speed up on the training time. And I'm sure it's possible. Like with the way diffusion works, it seems really simple. I'm sure there's ways we can explore
Mhm.
the diffusion training process and explore its different aspects and find things that can be optimized. I'm sure we can have like fast diffusion up and running as its own framework.
Yeah, so I think your main concern is just the training process. If we have better hardware, we can split the training process in parallel streams and learn from each stream. You can solve a lot of these problems. So the inference time is probably not a problem. So it's just once the training is much faster, definitely this can scale better. Yeah. That's actually I'm waiting for that as well. Like I see a lot of potential in this model, and I just want to see better, faster output for large language models. That's something that I like. So yeah, hope to see this model more successful.
All
Okay,
right.
if not, I'll just conclude. Yeah, overall, today we talked about the Mercury 2, which is a diffusion language model, and then we went to uncover behind some of the techniques how a diffusion language model might be trained using a denoising process that helps to recover back the signal. And also in the case of a language model, we also have an unmasking process to unmask some of the tokens. So overall, it's quite cool because it manages to do what other similar like latency models can do in a more efficient in a more accurate way. Just looking at this illustration, you can see that the scores are very, very competitive. Given that this is a diffusion model, it can compete with like reasoning models as well. And this is really going to be, I think, one of the key breakthroughs in the next few years. Once we can have faster latencies for large language model inference, we can likely be using it for a lot more domains, like in real-time systems, on edge devices. Maybe you can respond real time with robotic commands. I can see a lot of potential for this, so I'm quite excited for it. And yep, let's stay tuned for more updates for this. And with that, yeah, thanks for joining today's session. And I learned quite a lot from discussing with you all today, so thanks for coming. Hey, bye.